Hey, welcome back to Fat Mama Physics. In this video, we are going to go over a photoelectric effect question, which the experiment itself was done by Einstein, which led him to propose the photoelectric theory, and which paved the way for quantum mechanics. So you can almost say that Einstein is probably one of the grandfather of quantum mechanics himself. Irony is that later on he was one of the scientists against some of the later theories in quantum mechanics, including quantum entanglement, in which they call it the spooky action at a distance. So a very interesting part of history. So anyways, let's take a look at this example. At this point before starting this video, you should have a grasp of what the photoelectric effect. You should be aware of the experiment. You should be aware of what the photoelectric effect is able to show. Here, I just, this table here, hopefully you have filled out to a certain extent, in which hopefully you now are able to see how this experiment trumps over, or it goes against all of the classical views that we have about a wave, and it supports the fact that a particle can behave as a wave, a wave can behave as a particle, as well as a particle could behave as a wave, especially for very tiny particles, and how as well as a photon carries energy associated with its wavelength or its frequency, same thing, okay? So the photoelectric effect ultimately shows the fact that photons carry quantized amounts of energy. So they're little packets of energy that they're able to transfer to something else, in which that packet of energy is dependent on the frequency of light used. So in this example, I'm going to do questions A, B, and C. I will save for, you know what, I might do it in the same question. So I'll probably, do it in the same video. Hopefully I won't take very long. So let's begin right away. A metal is placed in a vacuum, and light of frequency f is incident on its surface, as shown here in the x-axis, in which the units are in hertz. Okay, always take a look at that part of the IB. IB likes to trick us with these numbers on the graph there. Okay, so there we go. As a result, electrons are emitted from the surface. The graph below shows the variation with frequency of the with the maximum kinetic energy of the emitted electrons, in which the units are in electron volts. So immediately you notice that there's a slope. It's a linear relationship. There's a slope to this graph, in which there is also an x-intercept, which is very interesting, which we'll talk about eventually. Question A. The graph above shows that there is a threshold frequency of incident light below which no electrons are emitted from the surface. Okay? With reference to the Planck's constant and the photoelectric work function, explain how Einstein's photoelectric theory accounts for this threshold frequency. Okay? So oftentimes, for students, I always find that they like to look at an equation, or they like to look at numbers and do calculations. Explain questions are always tougher. So you know what? Why not? Let's take a look at the data table to look at what is the applicable equations that we have here for this graph. So we have E max is equal to Planck's constant times frequency minus this little this phi symbol, which is the work function of the metal. And of course, the E is also the Planck-Einstein relationship for photons is here as well. Okay, so if you want to just have that on the side so that you kind of have something to work off of, go ahead. But of course, do whatever it takes to help you do a good job with this explanation. And when we ever have to do an explanation, explain, that's a key word there. Notice this is 4 good points. So again, it's always good to overkill an explain question than to undershoot it. So my approach, which may not be your approach, but one way you could approach an explain question, is to look at is to develop a flow chart for yourself, either on the side of the page or wherever else, before you actually start writing things down. It's kind of like a rough draft if you think about it. So what we want to do is we want to talk about what this threshold frequency is. So that should be my end goal. So let's make a little box here. This is the box I will use to just do my flow chart. So I'm gonna write F min, which is the minimum amount of frequency required to eject this electron from this metal surface. And what I want to do is I want to go from Einstein's photoelectric theory. So I'm gonna go from his theory to the I want to use that to explain the threshold frequency. And in my logical pathway, I need to make reference to the Planck's constant. So I need to make constant to this H. I also need to make reference to the photoelectric work function. So that's this guy over here. So hopefully you, by this video, you should know what they represent at this point. So in my explanation, I want to touch upon each of those things. So when we are asked to talk about Einstein's photoelectric theory, we should actually talk about it and say what it is before we even start the question. So it's like going from point A to point B. Okay, so we need to fully explain what point A is. Einstein's photoelectric theory talks about how light can act as a particle, which is a photon, which carries quantized amounts of energy. So that is his theory, and you should put that down. That's probably going to give you 1 mark, okay, even if you fail to explain the rest of the question. Okay, so here I just wrote light. It acts as a photon, and these photons carry quantized amounts of energy. It's very tiny, so hopefully, maybe I'll just zoom in here. Okay, so then we essentially want to go from point A to point B in our explanation. So how do we do that? It requires your full understanding of his experiment and the process involved. So Einstein's theory of light. To find out the amount of specifically amount of energy associated with this photon, we use the Planck-Einstein relationship equals to HF, in which the amount of energy carried by this photon depends on the frequency of the light, and H, which is the Planck's constant. And this is where in the question you can make reference to the Planck's constant as specified in the question. So then once we relate the photon of light to the energy, we can talk about then the minimum amount of work or the minimum amount of energy required by this photon in order to knock an electron off of a metal surface. So this photon carrying this work function, this minimum amount of energy is required to knock this electron off. So that this amount of energy has a specific frequency, which is our threshold frequency, involved, in which this minimum frequency is going to depend on the work function over Planck's constant as referred to earlier, okay? So that is how you make the link to the minimum frequency, and of course anything less than that minimum frequency means that no electron will be ejected. Okay, so that is the, so basically on my IB work page, I may just have a bunch of really messy writing just to help me kind of work through my explanation here. Okay, so now that I have that, I'm going to go ahead and write my explanation down, which is 4 marks. Okay, so let's go ahead. Okay, so here we go. This is probably overkill, and you might be thinking, oh, but you're typing, that's unfair. If you're writing with a pencil, you're definitely not going to be able to squeeze all this information down. I tend to over-explain when I'm typing because I see I have space. Of course, that you don't have the luxury. But what you can always do is if you go over the space that is provided in on an IB exam, you may, on the same page, continue our explanation somewhere else, as long as you make it very clear that that part of the page is tied to this part of the question, then that's okay. Worst case scenario, if you have a paper like this and then you have to explain on the back side because you're just absolutely out of space, you have to make that very clear. But try not to use a different leaflet of paper, because your IB exam usually gets detached and then parts of it get sent to other parts of the world. So that if you write it on, say, another leaflet, that may not be seen by the examiner doing the marking. So always use the same leaflet if you're trying to get extra space on the IB exam. You won't, unfortunately, be able to attach scrap paper to your work. But if you need extra space, use the same piece of paper, okay? All right, so what is this about? Remember, we're trying to go from point A to point B while making a pit stop at the Planck's constant as well as the photoelectric work function. So here we go. Einstein's photoelectric states that light behave as photons containing quantized amounts of energy related to the frequency of light in the following relationship. So good to define parts of the relationship, and since you have to mention Planck's constant, good spot to talk about that as well. And notice, stating the units and the numbers, it is good practice as well. In order for a photon to eject an electron off of a metal, a minimum amount of energy is required. This is called photoelectric work function, and I can't write the phi symbol, but imagine I could. It would go right here. Okay, this amount of energy carried by the photon is related to the threshold frequency needed. We'll call that F minimum for now, which is equal to the work function phi over Planck's constant, so that light having a lower frequency than that will not eject any electrons off the metal at all. Okay, so definitely overkill, but again, you're trying to get all 4 points, and usually those explain questions, it's kind of tough to get all 4 points, get the full marks. Okay, let's move on. You know what? I might have to break this off into a 2-part video because that was pretty long. Use a graph in A to calculate the threshold frequency, the Planck's constant, and the work function of the metal. So using this graph, and this is probably your favorite part of the question where you finally get to do some sort of calculation, you're going to use this equation from your data booklet. So what we want to do here is we kind of want to just match this equation to a y equals mx plus b setup, slope y-intercept form. Keep in mind this Emax is the kinetic energy for Emax, so that is going to be our y, and here we're going to have hf, and since f is our x-axis, that's going to be your x, m is going to be our slope, which is our Planck's constant, mx plus b, but since this is minus the work function, our b value is going to be negative. So it makes sense, because if you think about it, the y-intercept is going to be somewhere down over here. Okay, so let's take a look at what we have defined. First of all, we need to find the threshold frequency. Now, it doesn't seem like we're going to be able to do that from this equation. But if you think about it carefully, if you supply just enough energy for the electrons to escape the surface of the metal, think about how much kinetic energy those electrons would have. So if you think that these electrons will have 0 kinetic energy and they'll be just ejected, then you are correct. With an Emax or kinetic energy of 0, we can then use that to figure out how much frequency we need. So, well, it says here we have to calculate. But I think we can just safely go ahead, and since it is very obvious, we have to just use the x-intercept here. Or you could, just for safety, you could say that when Emax is, or EK equals to 0, this is going to give you the threshold frequency. sorry, the writing's very messy, but you could just write this, just a sentence just to explain your line of thinking if you don't feel comfortable just stating this fact. Because it looks like this 1 mark just means you have the correct answer, okay? So what would this be? This is right here. The graph intersects the x-axis right there. So it looks like this is divided into 2 boxes equals 2.1. So that's going to be 1.1 times 10 to the power of 15 hertz. You may also use units of seconds to the -1 as well. Both work out. Okay, so there you go. Okay, question B1. B2 is the Planck's constant, and as previously explained, this is the slope of the graph. So you should definitely show that you understand that, even if you got the incorrect value of the slope. So you may even write a note down, slope of graph, so your examiner knows what you're trying to do. And you know what? Try not to do the slope on your head. Actually try to show some working on the graph by finding the slope, because sometimes even if you get the wrong answer, if the examiner sees that you're using the slope of the graph, you may get awarded marks for those type of questions where you have to find the gradient or the slope, okay? So here, to find the slope, I'm going to take this point here, which is very easy to calculate. And I am probably going to use this point here, which is a nice enough point which intersects the axis here. Intersects the grid line, sorry. So that's going to give us a difference of 1.9. That's going to give us a difference of 1.00, so that's going to be 0.9. Feel like I'm not doing my math correctly. But anyway, 0.9, yes, 0.9 times 10 to the power of 15 hertz as my base, and my rise is going to be 0 all the way to 3.8, if I'm correct. 3.8 EVs. Okay, so that's the slope of my graph, and that should give me H for my Planck's constant. But I just have to be very careful that this is an EV and not in joules. I do have to do that conversion there. So let's go ahead and do that. Okay, so I'm going to convert the EVs into joules, I'm going to multiply it by 1.6 times 10 to the power negative 19 joules per electron volts. And this is going to give me, okay, and then also I'm going to divide by the 0.9 to the power of 15 right now. Oof, and it gives me 6.75 repeated times 10 to the power of negative 34. And this is going to leave me with units of joule. Seconds are going to go on top. Joule seconds. In fact, I could have done a better job in showing my work here, because notice it is 4 marks, meaning that we probably should have 4 really good pieces of steps involved here in calculations, which I imagine is going to be a lot easier than figuring out what we're missing in, say, an explain question. So one thing that we did show over here is this working, which we didn't include down there, but we actually used it as part of the work that we were showing. So I'm going to need to move that down to where I've shown the working. I know it's not the same thing if you're trying to write things down on paper. You can't just move it like that, which takes away other stuff. So you know what? I'm just going to write it again because that's not very well done. So to complete the work shown here, I could have shown this step here to show that the fact that the slope is indeed the Planck's constant, but also to include the fact that the slope uses electron volts per frequency, or times seconds per hertz. So I should say that the slope multiplied by the elementary charge, or the electron volt 1.6 times 10 to the power negative 19 gives me the Planck's constant. So this work over here that I just did, this work should have been shown before I started doing any calculations, okay? So yes, since it is a 4-mark question, you probably want to show a little bit more work and not just jump straight into calculations like I did, okay? So, okay, I'm showing the mistakes I could make, and so hopefully you don't make them. I'll be your negative example. Okay, number 3, work function of the metal. Okay, so again, it's, yes, it is 2 marks, but let's just practice showing work here. For the work function of the metal, according to our previous equation, so let me just write it again for completion's sake. So from this comparison, we can see that the y-intercept here is going to give us our work function. And, from the graph itself, that's not going to work out because it shows that it doesn't show the y-intercept below the x-axis, meaning that we're going to need to use other aspects of the graph to help us calculate the work function of the metal. So if we use the equation, which means that we need to use a different way to figure out the work function without the y-intercept. So going back to EK equals to, going back to this equation here, with figuring out the work function, we know that the minimum kinetic energy that we need is 0. So in order to be ejected, the electron does not necessarily need any kinetic, residual kinetic energy. So this can be 0, meaning that whatever we have left over, if we put the work function to the other side, we get the work function is equal to Planck's constant times the frequency at that location. So we have to be very careful here. The frequency is, again, we're using our graph. The frequency we use from question I. This guy over here, that's the threshold frequency. This is the second part, which is Planck's constant. This is also where we have to be careful because we have to we have to be integrous to the graph, since the question did say the graph. And technically speaking, if we did extrapolate to the y-intercept, this work function would depend on the Planck's constant we grabbed from the graph itself, which is 6.75 repeated times 10 to the power of negative 34, and not the one from our data booklet. So please don't use the h in our data booklet. It needs to stick true to the graph, meaning we're gonna use the h from the graph, and no rounding here, as well as the threshold frequency we found in I, which is 1.1 times 10 to the power of 15 seconds to the power of negative 1. So putting all this in, we're gonna get 7.43 times 10 to the power of negative 19 joules. Rounding off to about 2 significant figures, oopsies, that's going to be 7.4 times 10 to the power of 19 joules, okay? Okay, so that's it for this graph. This next bit of the question here, it's actually, I'm going to do it in the next video. It's not an IB question. I've attached it to this question itself as an extension to really flush out the our understanding of this topic, okay? So, thank you for bearing with me. I thank you for watching Photoelectric Effect, and I wish you the best of luck, and Thermophysics signing out.